This shouldn't exist. Deep beneath Japan's mountains, engineers are building a train unlike anything the world has ever seen.
At full speed, it reaches 603 kilometers per hour, faster than conventional rail, faster than many aircraft during takeoff. But speed is only part of the story. The real challenge lies beneath the mountains, standing between Tokyo and central Japan. Engineers could have gone around the mountains. Instead, they decided to go straight through them. What happened next transformed a transportation project into one of the most expensive engineering programs ever attempted. The project began with an estimated cost of $9 billion. Today, estimates exceed $72 billion and continue to rise. 86% of the railway runs underground. Few infrastructure projects have ever attempted anything on this scale.
Behind me, this massive boring machine is cutting through solid rock to create one of the largest tunnels in the world.
The geology is ancient. The pressure is extreme. Underground rivers flow where no one can see them. Engineers said it would be difficult. The mountain had other plans. For decades, Japan's famous bullet train transformed transportation. But success created a problem nobody expected. The Tokaido Shinkansen became one of the busiest rail corridors on Earth. Demand kept increasing every year.
The challenge here is unprecedented. With millions of passengers daily, optimizing the flow is crucial to preventing system-wide congestion.
Japan needed a second route. Something faster. Something capable of carrying future demand. The answer would become the Chuo Shinkansen, a railway unlike anything ever built before. The story actually began before the first bullet train entered service. Japan was already looking beyond conventional rail. In 1962, researchers began investigating magnetic levitation. The idea sounded impossible. A train without wheels at high speed, no engine on board, no traditional traction system.
The solution was revolutionary. Instead of pushing against steel rails, this train would float above the track.
On paper, the physics worked. But turning equations into a railway would take more than 60 years. To prove the concept, Japan needed more than calculations. It needed a real track, a real vehicle, and real-world testing. In 1977, the first experimental Maglev track opened in Miyazaki. Just 7 kilometers long, but it would change transportation forever. For the first time, engineers witnessed stable magnetic levitation outside the laboratory. The train actually floated. The achievement validated decades of research. But one successful test was not enough to build a national railway.
But magnetic levitation was only the first step. Engineers wanted higher speeds, longer routes.
The next challenge was obvious. If Maglev was going to connect major cities, it had to survive Japan's toughest geography. In 1990, geological surveys began across the Japanese Alps. Engineers were searching for a path through solid rock. The surveys revealed a harsh reality. These mountains were older, deeper, and more unpredictable than expected. Some sections contained fault lines. Others hid underground rivers. Every discovery increased the project's complexity. 19 years of surveys followed. Before a single major tunnel was approved, engineers needed answers.
After decades of preparation, approval arrived. Construction could finally begin.
Before building the main line, engineers needed one final proving ground, the Yamanashi test track. This was no small experiment. More than 18 kilometers of full-scale railway were built for testing. Every component was tested: levitation systems, guidance systems, propulsion systems. Nothing was left to chance. Then came one of the project's most important innovations. The guideway itself became the motor. Unlike conventional trains, the engine would not travel on board. It would be built into the track. Figure 8 coils installed along the walls handled levitation, guidance, and propulsion simultaneously. The tolerances were extraordinary. Every section had to be aligned within millimeters across kilometers of track. Even tiny deviations could affect stability at 500 kilometers per hour. The technology was working, but building a railway through mountains would prove far harder than making a train float. Construction began with a simple goal: reach Nagoya as directly as possible. But the shortest route crossed some of Japan's most unforgiving mountains. The railway would stretch 286 kilometers between Tokyo and Nagoya. An astonishing 246 kilometers would run inside tunnels. Engineers quickly realized this wasn't a railway project. It was one of the largest tunneling projects ever attempted. Some mountains contained more than 1,400 meters of rock above the tunnel. That's taller than most skyscrapers on Earth. The first excavation crews entered rock that had remained untouched for hundreds of millions of years. At first, progress was steady. Drill, blast, remove debris, reinforce, repeat, day after day. Then the geology refused to cooperate. Rock conditions changed without warning. Schist formations shattered unpredictably. Some sections behaved nothing like geological models predicted. The mountain had other plans. Engineers were forced to stop and rethink entire sections of the route. What happened next cost billions. Tunnel boring machines could no longer continue through some areas. Instead, crews switched to the new Austrian tunneling method, a slower but more adaptable approach. Steel ribs were installed, then shotcrete, then rock bolts, then more shotcrete. Layer after layer of protection. Progress slowed dramatically. Some tunnel sections advanced only a few meters each day. Then another challenge appeared. Underground rivers began flowing directly into excavation zones. In some locations, crews pumped more than 10,000 liters of water every minute just to keep working. Engineers developed drainage systems, grouting techniques, and waterproof barriers to regain control. Across the route, dozens of construction sites worked simultaneously. Every delay threatened the schedule. More than 30,000 workers became part of the project. Most would never ride the train they were building. While tunnels advanced, engineers carved entire railway stations directly into solid mountain rock. One cavern became larger than many surface stations. 40 meters underground with no natural light, a railway terminal was taking shape. After years of tunneling, the focus shifted from digging through mountains to building the system that would make the train fly. Every guideway section had to be positioned with extraordinary precision. The tolerance was just 1 millimeter over 50 meters. Then came the coils. More than 580,000 individual electromagnetic coils would be installed throughout the route. Together, these coils create an invisible magnetic highway. They lift the train, guide it, and push it forward. But the most remarkable technology isn't in the track. It's hidden inside the train itself. Each train carries superconducting magnets cooled by liquid helium to nearly absolute zero. At minus 269 degrees Celsius, colder than the surface of Pluto, electrical resistance nearly disappears. Below 160 kilometers per hour, the train rolls on rubber tires. Above that speed, everything changes. The tires retract, the train rises, contact with the guideway disappears, the vehicle begins to float. Engineers spent decades refining this moment. Now it was time to push the technology to its limits. Test speeds climbed higher and higher, 200, 300, 400, then 500 kilometers per hour. Then came the breakthrough. On April 21, 2015, the train reached 603 kilometers per hour, a world record. Inside the train, passengers reported surprisingly little vibration. At 600 kilometers per hour, they could still read a newspaper. The railway had proven itself, but another obstacle was waiting above ground. A dispute over groundwater in Shizuoka Prefecture stopped construction for 4 years. One governor's refusal delayed the project and added billions of dollars to its cost. Eventually, construction resumed. but by then the estimated cost had climbed beyond $72 billion. When complete, the railway will cut travel time between Tokyo and Nagoya to roughly 40 minutes. Seismic sensors, automatic braking systems, and earthquake monitoring networks are designed to protect every journey. For more than 60 years, Japan chased an impossible dream. Soon, a train will float through mountains at 500 kilometers per hour, turning science fiction into reality. The mountain that once stood in the way has become part of the railway itself.